Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems at the University of Michigan. This is our 11th lecture of the winter 2022 semester, where the topic of today's lecture is going to be on inverse kinematics and the role that inverse kinematics plays within our robot operating system, so how we can configure our robots to solve some desired end effector position. And so before we get started, I'm going to go ahead and minimize myself so we can all see the slide content.
All right. So to begin today, we're going to talk about a couple of administrative points before we get into inverse kinematics. So the first thing I want to mention is that assignment 3 on forward kinematics is going to be due this coming Friday, February 18th at 11:59 p.m., following the standard process of grading based on the CI grader. The second thing I want to mention is that we have a new quiz policy for late quizzes. And so I've mentioned this in the recent interactive sessions and during lab, but I just want to reiterate it here during lecture so that everyone's aware that we are now accepting late quizzes, including quiz 1 through 3, and the late quiz the late policy will follow the same policy that's used for projects, so up to 80% of possible credit within 2 weeks, 60% within 4 weeks, and 50% as long as it's submitted by the end of the grading period. And then one thing to remember is that now that we're accepting late quizzes, we can't discuss quiz questions directly on Slack, but you can feel free to direct message the course staff about quizzes or come to office hours, and we can discuss the answers if you have questions. So the way that these late quizzes will be administered is there will be a specific new assignment on GradeScope, which is called like Quiz 1 Late. If you take the regular quizzes, you don't need to worry about that late quiz option. But if you want to take the late quizzes, those will be open until the end of the grading period. The second thing that I want to announce and kind of reiterate from when I've announced it during interactive sessions in lab is to remind you that for assignment 3, there's this new robot definition feature. And so to clarify the details of how that feature is going to be administered, we have it summarized on this slide and also described on the project spec. So in particular, you're going to be working in pairs of teams of 2 to implement this new robot definition. And so the way that this will work is actually, it's sort of this Wednesday, so February 16th, the same Wednesday that this lecture is being released, we have dedicated course time for our paired programming to actually work on these features yourselves. So if you are looking for a student, I'd recommend coming to lecture, and we can find a student that you can be paired with. Alternatively, we have a channel on Slack where you can find partners in the assignment 3 channel of our Slack workspace. And then next Wednesday is when we're going to have our robot showcase. So everyone in class is going to present their new robot definition to the class and demonstrate that it works with forward kinematics. And so we ask that you push your new robot description to your repositories by the start of the interactive session next Wednesday. And to encourage everybody to come out, we're also going to have pizza during that time to go along with our robot showcase. Okay, so one other thing that I want to mention and sort of foreshadow is the potential for your Knievel stencil and your implementation so far to work with a real robot. So in particular, if you have your forward kinematics working properly with the fetch robot, then we can actually begin working with real robots, with real physical robots. And so the way that we can do this is by pairing our Knievel stencil with the Robot Web Tools ROS bridge, which will let us interface with the physical fetch robot and communicate with it. So in particular, what this looks like is we can actually have the fetch robot, our physical robot from our lab, communicate its joint configuration state to your Knievel stencil, and your Knievel stencil then can render using forward kinematics the current state of the robot. So just as shown in this picture here, you can see the Knievel stencil is reflecting exactly what the state of the fetch robot is. And so normally during sort of non-COVID-19 semesters, the way this would work is everyone would have a chance to connect their Ford Kinematics code to our real physical fetch robot. Students in the past would sort of take a picture with it as sort of a souvenir from the class. And so we're going to try and offer this semester. So as an optional kind of feature. And so for those who are interested, we ask that you let us know. So over Slack, we'll make a sort of a thread that you can, or a message that you can react to, just to kind of gauge interest for how much time we should dedicate to this potential. And then following winter break, we will have dedicated time during the interactive sessions where we will have the physical robot in place and available for you to connect your Knievel stencil to. All right. So to begin now, let's start talking about inverse kinematics by first recalling what we've talked about on the topic of forward kinematics. So in particular, you'll remember that our forward kinematics discussion began with our linear algebra refresher, which then led into the two lectures we had, lectures 7 and 8, on forward kinematics, which demonstrated how it is that we can infer the pose of an end effector of our robot given the state of each joint. Whereas inverse kinematics, which is what we're going to be talking about today, allows us to infer the joint states necessary to reach a desired end pose for our robot end effector. And so within our robot operating system, both forward kinematics and inverse kinematics can be thought of as sort of core modules that we would want to have implemented. And so as a refresher about where we stand within our course, so you'll recall that we discussed the various modules that you might want within a robot operating system. Some of the possible kind of modules and functionalities are defined here on this slide, where in lecture 2, we discussed path planning, which was our first assignment. We then discussed feedback control in lectures 5 and dynamical simulation in lecture 4, which became the foundation for our assignment 2 and our implementation of our pendulum and PID controllers. And so now we're on the topic of forward and inverse forward kinematics for assignment 3, which we discussed in lecture 7 and 8. And that brings us now to today, where we're going to be discussing inverse kinematics during this lecture and next lecture as we prepare for assignment 5. And then upcoming, we'll be discussing some of the other modules that are described on this slide and highlighted. So within forward kinematics, just as a refresher, we said that it's a many-to-one mapping of robot configuration to reachable workspace of the end effector. So another way of expressing that or thinking about that is our goal of being able to find some transformation that would describe the position of the end effector with respect to the world frame, so that T sub 6 superscript 0, from the given joint angles of the robot arm, right? So our goal in forward kinematics is to be able to find this transformation based on each of the joint angles describing the let's say, angle of rotation and prismatic translation of each potential joint along the kinematic chain. And in contrast, inverse kinematics is going to flip that around. So in inverse kinematics, our goal is to find the description of the joint configuration. So we want to find the angles or the prismatic degree of translation based on some given pose of the end effector with respect to the world frame. And the reason that that's useful is because, for example, if we want to execute some task of our robot, so if we want our robot to pick up an object from on top of a table, or we want our robot to open a cabinet and things like that, then those tasks are going to be defined based on the position of the end effector in the world coordinate frame. But that alone does not then allow our robot to actuate that task, to actually produce some control policy to move the end effector to be able to pick up that object or to open the cabinet. We need to actually express, just like for our PID controller, the desired angle or the desired prismatic translation of each of these joints. And so that's the purpose of inverse kinematics. Inverse kinematics is going to allow us to solve for these joint configurations based on this desired pose of the end effector. And so when we think about how it is that we could potentially implement forward kinematics, there's these two possible approaches that we could think about. So the first approach, which is what we're going to be discussing today, is what can be thought of as a closed form solution, where we're going to use knowledge of the geometric properties of our robot to directly infer some satisfying configuration for the end effector pose based on those geometric constraints. And so the advantage of a closed form solution is that typically these will be very efficient. Because of that closed form nature and because we have such knowledge of the geometric constraints, this can typically be computed in constant time. In addition to that, closed form solutions are very nice in that they have predictable solutions, so we can be guaranteed, or we can at least be very confident that we will find some valid configuration based on our knowledge of the robot's physical constraints. However, one downside with closed form solutions is that they tend to be brittle in the sense that they will be sort of specific to a specific robot or a specific kind of structure within robot kinematics. And so to kind of broaden the applicability of our inverse kinematics, an alternative approach would be to solve for inverse kinematics using some form of optimization, where we would be trying to minimize some notion of error of the end effector's pose with respect to the desired pose by modifying the joint configuration that we are trying to solve for. And so often you will use some form of gradient descent to perform this optimization, which has a nice property in that it's very general, right? So that you could apply that same technique to a broader variety of robots and kinematic structures. The downside is that you'll lose some of the speed potentially, or at least the predictability in the sense of a guaranteed sort of global optimal solution using the solve by optimization technique. And so once again, so for today's lecture, we're going to be talking about closed form solutions, and then next lecture, we will talk about approaches to solve inverse kinematics using optimization. So to lead into our discussion on inverse kinematics, let's first go back to forward kinematics, and let's use our definition of forward kinematics to set up the problem of inverse kinematics. And so to motivate this, one really cool and exciting example of kind of directly where our discussion of inverse kinematics can be seen is on the what's called the Canadarm, which is used within the ISS for doing tasks within space. So a slightly simpler example, which will ground our discussion, is the two-link planar pendulum arm that we've talked about in the past lectures. And so we'll use this setup to start by defining and kind of refreshing our definition of forward kinematics, and then directly define what inverse kinematics is attempting to solve and a closed form solution of inverse kinematics in this two-link planar arm scenario. So as a refresher, so the planar two-link arm, so it has two rigid body links that have some known length, and in addition then, it also has two articulated rotational joints. So there's two joints, each of which have a coordinate frame, and that coordinate frame is then defined, as you can see on this slide, with the red highlighted axes. And these coordinate frames then can be transformed based on the two angular degrees of freedom that exist within the revolute joints. And so in this robot arm, the robot configuration is defined by that by those two rotational degrees of freedom, which we're going to define as being the variable q. So q contains theta 1 for the first rotational joint and theta 2 for the down chain second rotational joint. And so finally then, what we're interested in forward kinematics is, of course, the position of the end effector. So in this case, our end effector for the planar two link arm is that point at the very end of the arm itself. And so once again, this end effector also has its own frame of reference, which is highlighted by the red axes at the end of the arm. And so if we put all these pieces together, this slide then summarizes this full setup. So we have our robot end effector, which we can think about as being like the gripper pose within the world frame. And this gripper pose is defined by both a position within the world frame of reference. So we're going to call that position to be this point O in the world frame 0, which we're going to also interchangeably call that with P superscript 0. So 0 is denoting that it's in the world frame of reference, and it has two components in this planar case. It has an X component and a Y component. So that's the first component of what we call the end effector pose, right? So it's this position. The second component of the end effector pose is an orientation of the actual frame of reference of the end effector. And so this rotation here is going to be described by R superscript 0 sub n to denote that it's the rotation converting from the nth frame of reference, which in this case is 2, to the 0th frame of reference, which is our world coordinate frame. And so the end effector then defines this sort of tool frame of reference that has some transform to the world frame of reference. And so by specifying both this point of the end effector's position and also the rotation of the end effector, we will have defined the final pose of our end effector in the world coordinate space. And so typically when we think about these end effector axes, the way we can think about it is that they'll sort of align with the actual tool that the robot has access to. So in the case of a gripper tool, the actual axis of this gripper tool would be defined, for example, with respect to where that gripper action can take place. And so then using knowledge of where this end effector axis is within the world is what it will ground our actions that are made using the tool of the robot, right? So in the case of the gripper, if you know where this end effector axis is, then you know exactly what closing the gripper at its current position would result in for task planning within our robot. So as a checkpoint, here's kind of a question just to make sure that that we're sort of following this notion of transformations between different frames. So let's consider again this case that we have some robotic gripper that has an end effector with a gripper tool on it, and let's say that this robot is part of some multi-link arm, which is shown here. So still let's say a planar arm. And so what we're interested in knowing with forward kinematics is the position of our end effector in the world coordinate frame. And of course, the way that we can do that is by chaining together our transformations from the parent joints and links in order to define our forward kinematics routine and transformations. So the checkpoint question here would be if I want to calculate this end effector in the world coordinate frame, and I'm given, let's say, some local definition of the end effector in some link n frame. So here there's 4 links, so we could say the end effector position with respect to link 4. What would be the transformation to find this end effector in the world coordinate frame? So you can pause the video and just see if you can recall this or kind of remember this. This one's not a trick question. So now that you've had a chance to think about it, right? So in our notation and the way that we've set up our forward kinematics, the way that we can calculate this position of the end effector in the world coordinate frame is by taking the position of our end effector in some link n frame, so in this case link 4 frame, and then applying the transformation, which takes us from that link n frame to the world coordinate frame. Right? So this was the whole sort of setup and motivation for applying our Ford kinematics routines is the approach by which we calculate this transformation matrix. All right. So to summarize Ford kinematics, the whole purpose behind it was to say, here's some given robot configuration. So here are the joint angles of our planar two-link robot, right? So let's say that theta 1 takes on some value, theta 2 takes on some value. I want to be able to compute where the end effector is within space as defined by the world coordinate frame. And so from that given configuration, what we want is some function that will take that given configuration and produce the position and then also the orientation of our end effector within the world coordinate frame, right? So the whole purpose behind Ford kinematics was to say, here's some configuration, apply some function f, which in our assignment 3 was our recursive Ford kinematics routines, in order to produce the resulting position of our end effector and the orientation of our end effector in the world coordinate frame. And so we can think about it in this functional form to help ground this notion of Ford kinematics. And so one thing then that we can start sort of, another way we could pose this, or just kind of reiterating, right? So Ford kinematics is asking, what is the position and what is the orientation of the tool of our robot with respect to the world coordinate frame? And so we can then think about this in the case of the planar two-link pendulum arm as being, again, this question of where is our end effector in the world coordinate frame, so P superscript 0, based on the transformation from the end effector frame, which is in frame 2, back to frame 0, multiplied by the position of the end effector with respect to its parent link, which is link 2 in this case. And so this is what our Ford kinematics is attempting to do. It's attempting to calculate this composed transformation from frame 2 back to the world coordinate frame 0. And so the result of this is going to be our ability to calculate both this vector describing the position and also this rotation matrix describing the orientation of our end effector. And so we can think about this a little bit, and we can, using this goal of describing this composed transformation, the first thing we can do is we can observe that to calculate this position in the world coordinate frame, we can think about it as first rotating this position 2 based on the rotation from frame 2 to frame 0, and then finally translating it based on the translation of frame 2, where this composed rotation here from frame 2 to frame 0 is the composed rotation of frame 2 to frame 1 and then frame 1 to frame 0. And so if you work this out, it turns out that in the case of the two-link pendulum arm, this rotation from 2 to 0 is going to be defined in this fashion, where we can think about it as simply adding together the theta 1 and theta 2 for the two revolute joints. So this is the standard rotational matrix definition, where the angle of rotation is the composed theta 1 and theta 2. And so if you're wondering whether or not this is actually the case, or whether we need to actually compose these rotations explicitly, it is the case. So you can actually work out that those rotations will compose in that manner. So that gives us our orientation, and the next thing then that we're interested in is the position of our end effector in the world coordinate frame. So to work through that, so what we can do is we can start with this equation that we have for calculating the translation from frame 2 to frame 0, and simply by using substitution and then some trigonometric identities, we can actually calculate this position. So I'd recommend pausing the video here and seeing if you can work through this first, and then then we can talk about the approach. So now that you've had a chance to sort of pause the video and try working through this, so the first step here that we're showing is simply rewriting essentially this equation that we have given here. So we have the rotation from frame 1 to frame 0, which is based simply on theta 1, multiplied by this translation, which you can calculate using the known lengths of the links with the trig properties of the second rotational joint, and then similarly the link of length 1 by the rotational properties of the first revolute joint, and then using these trig identities, you can actually simplify the position vector into this form here. And so I won't step through each of those calculations, but it should be. But essentially, the terms here with alpha 2 represent what was essentially the matrix vector multiplication within that last slide. So those two matrix multiplies, basically those dot products within the matrix multiply, are what results in these two alpha 2 terms, and then the alpha 1 terms are what's left from that final addition of the translation vector that we had from link 1. But with that, these two components, so this position vector describing the position of the end effector with respect to the world coordinate frame, and this rotation transformation, which can describe the pose, or the orientation of our end effector with the world coordinate frame, these are the two outputs of our forward kinematics. And so with these two outputs, we can understand, given the joint configuration, where is the end effector, right? And so I'll just point out that, again, the only variables that are needed to actually calculate both the orientation and also the translation are theta 1 and theta 2. In addition to that, we have alpha 1. And so we could think about the kinematic structure of our robot as also being needed as input, as part of this configuration queue. But it's really, if we have theta 1 and theta 2, if we know the joint configuration state, then you can perform forward kinematics. So to summarize, our forward kinematics that we just walked through is going to result in the composed transformations that we were interested in to begin with. So we'll be able to transform our position of the end effector into a position of the end effector in the world coordinate frame using this composed transformation from frame 2 to frame 1, and then from frame 1 to frame 0, where that composed transformation is a function of the joint configurations defined by theta 1 and theta 2. And so this is exactly what we set out for in our forward kinematics setup, which now leads into our inverse kinematics setup. So in inverse kinematics, instead of being given the joint configuration and trying to compute the end effector position and orientation, we're instead going to be given the end effector position and orientation and be asked to compute a joint configuration that would satisfy it. And so in kind of graphically, what this is going to look like is we're going to be given this point here, and we're then going to be asked to solve for theta 1 and theta 2 in the case of our two-link planar arm. And so if we think about this in sort of functional form, one way that we could think about what it is that inverse kinematics is trying to solve for is it's trying to define this inverse function f, which instead of taking in theta 1 and theta 2 to produce some end effector pose p, instead this function f inverse is going to take in the end effector position p and try to calculate theta 1 and theta 2 that would satisfy the end effector being at that specific position. And so for now, for our discussion of inverse kinematics, we're going to focus just on the end effector position, and then we can come back to the end effector orientation in the future. And so to start with, before we start trying to solve for the inverse kinematics for our two-link arm, it's helpful actually to begin with our 1 degree of freedom pendulum from assignment 2, and think about what inverse kinematics would look like in this simplified case. So in particular, so the setup for inverse kinematics in the 1 degree of freedom pendulum case is going to be like that we're given some desired end effector position, which is going to be specified as an XY location, and we want to be able to calculate what the angle of rotation is for our revolute joint that would satisfy the end effector being at that XY location, right? So in other words, what is theta 1 in this diagram, given that the end effector should take on some position at an x coordinate and y coordinate, where once again you'll recall that this theta 1 describes the degree of rotation about the rotational axis, which is defined according to the 1 degree of freedom revolute joint that really defines our pendulum. And so you can pause the video and think about this question if you want. Once again, this one's not a trick question, so it's probably apparent that we can calculate this theta 1 using trigonometric properties of our pendulum geometry and kinematics, right? And so in particular, what we can do is we can recognize that if we know the x-coordinate and the y-coordinate of our desired end effector position, which is shown in this blue point here, we can calculate the angle of rotation that would position our end effector at that location based on the inverse tangent function. So using the inverse tangent function, we can directly calculate this theta 1. And so this inverse tangent function in the case of the 1 degree of freedom pendulum would exactly solve for our problem of inverse kinematics, right? So this would produce the joint configuration, which in this case is just theta 1, given as input simply the end effector's desired position as expressed in these coordinates. So given that we see we can solve this inverse kinematics in the case of a 1 degree of freedom system, let's now move to the 2 degree of freedom planar arm that we've been talking about, and let's see if we can solve for both theta 1 and theta 2 in this slightly more complex kinematic structure. So to start with, for our inverse kinematics in the 2-link arm, we'll first start by trying to solve for theta 2, so just the second angle of rotation, and then we'll come back and solve for theta 1 after we have done that. And so once again, in this setup, just like we looked at in the 1 degree of freedom case on the last slide, the input to our inverse kinematics routine is going to be the x-coordinate and the y-coordinate of our desired end effector position, and from that x-coordinate, y-coordinate, we're going to try and calculate theta 1, theta 2. So to start with trying to calculate theta 2, let's see if we can work through this. So the first thing that we can observe is we could describe theta 2 with respect to its supplementary angle as defined by this x1 axis. So in other words, while it seems like maybe initially theta 2 it's not obvious how we're going to calculate theta 2 given this x coordinate, y coordinate, let's try and incorporate some additional information by relating theta 2 to this supplementary angle, which is defined according to the axis of x1. And in particular, what we can do is once we kind of define this supplementary angle, we can use the law of cosines in order to actually calculate this supplementary angle. So in particular, if we essentially, so the way to visualize this is to think that this point C is positioned here at the origin of link 2. And so what we're going to be able to calculate then is this supplementary angle, simply given this equation, with where A, B, and C can be calculated using the known lengths of the pendulum links. And once again, so if we essentially plug in the lengths of those links, we'll get out this supplementary angle. And at that point, because we know that it is a supplementary angle, we can then directly calculate theta 2 simply by essentially subtracting 180 degrees from the result of our calculation. All right, so at that point, we'll have solved for theta 2. And the next thing then that we have to do is solve for theta 1. And so theta 1 is, and I should mention also, so in addition to using the pendulum lengths, that's right, we also use the position of the end effector in order to calculate this, the the sort of base of that triangle, which was C in our law of cosines equation. So you can see we're incorporating information about the position of our end effector in our calculation here for theta 2. Okay, and so given theta 2 now, so the other degree of freedom that we need to solve for is theta 1. And so let's see if we can think about how we can do that. One thing I'd recommend is maybe try pausing the video. So given that we've worked through one of them, see if you can work out what trigonometric properties of this setup here could be used to allow us to actually solve for this theta 1. So I'll give you a chance to pause it and see if you can work it out before I move on. So now that you've had a chance to think about this, let's take a look at how we could solve for theta 1. So the first thing that we can do is we can realize that that this theta 1 here is at least it's related to this larger angle that could be expressed between x0 and the vector pointing to our end effector in the world space, the vector that's highlighted by this kind of chalk red line. So that arc that here is shown by this blue arc, that angle we can calculate just as we did in the 1 degree of freedom pendulum case. So if we use inverse tangent, we know that we can get this larger angle here. And so at that point then, we can realize that if we expressed theta 1 as the difference between that larger angle that we just calculated and then this remaining component here, which we have not calculated, we could solve for theta 1. So we could say theta 1 is going to be equal to this larger angle minus this remainder here. So then the next thing that we can try and do is we can try and calculate, well, what would the remainder be? And it turns out that we can do that also using inverse tangent and some additional trigonometric properties. So we have that calculation here. So once again, it's essentially using the same kind of idea where we're going to take inverse tangent based on the opposite component and then the adjacent component, which we're calculating here, and then the result of that is we have theta 1. And so once again, one thing to kind of recognize is that in both equations for our theta 2 and our theta 1, the inputs are the desired position of our end effector expressed as x and y, and then also the known length of the pendulum length. So that's alpha 1 and alpha 2. The other input that you can see we have for our calculation of theta 1 is actually our angle theta 2. And so the reason that that's valid to do is because our calculation of theta 2 does not depend on theta 1. So we can solve for theta 2 first and then plug in the results for our calculation of theta 1. And so from that, we will have calculated this inverse function f that we were interested in, right? So we're now going to have an approach to solve for theta 1 and theta 2. But one thing that is good to think about would be like, is this guaranteed to be the right solution for any x, y that we plug into our function? And so this is kind of like an interesting set of things to really think about here. So the first thing that's worth pointing out, right, is if we give it some desired position for our end effector, it might not be the only solution, right? So there's this case, for example, where if we think about this as being like the middle joint as being like an elbow, for a specific end effector position that we might plug in as being desired, there would be these two different solutions that could both satisfy that end effector position, right? So you could have like elbow up, elbow down. In addition, right, we could then sort of ask, well, would there be a case where there's guaranteed to be only a single solution, right? So would there ever be a case where we would input a desired end effector position and we get out a guaranteed unique theta 1, theta 2? So the answer to that is that yes, there is a case where we could have a unique guaranteed solution, and actually there's an infinite number of cases where the distance from the desired end effector to the base of our pendulum arm is exactly equal to the total length of the two links added together. So if and you can think about this as there's no case here for that sort of elbow up, elbow down property where you have multiple solutions. Another interesting case then is to ask, would there ever be a situation where we could input some desired end effector position and there is no solution produced by our inverse kinematics routine? And the answer to that is actually yes. There are cases where for our inverse kinematics routine there will not be a defined solution. In particular, if we position the end effector such that based on the pendulum lengths, they could never reach this. They could never reach this angle, this end effector position. And so this is one thing to think about when we think about inverse kinematics routines, is that we are trying to solve a constrained set of equations by basically modifying a set of variables that are unknown. And so anytime that comes up, the number of unknowns and the number of constraints that we have are going to determine whether the system is overdetermined or underdetermined, which can again affect whether or not there are unique solutions or no solutions to the actual system. And so this is something we'll talk more about, more in this lecture, but it's also something we talked about during our linear algebra refresher, you'll recall. And so on the topic of inverse kinematics, this is really crucial because if we want our robots to be able to operate, of course, having no solution to an inverse kinematics routine can be problematic for the robot to actually actuate tasks. So now that we've looked at inverse kinematics for the 1 degree of freedom case and the 2 degree of freedom case, of course, the next question to ask is what about the 3 degree of freedom case? So could we do inverse kinematics for 3 lengths? And so it turns out that we can. And if you're curious, kind of a fun example of this where you can actually test sort of your own kind of internal controls as an attempt to solve inverse kinematics, there's this cool example project here. So if you go to this link, it'll take you to this game where you can try and control this 3-link pendulum or this 3-link arm to reach the set points. So what you would be doing if you play this game is you're trying to actually solve inverse kinematics yourself. And it's a nice illustrative example actually of how challenging inverse kinematics can be, because I think when I play this, I can get like around 11 to 12 of these set points reached in, I think the timer's for like a minute or whatever their set timer is. And I think the world record, like last time I checked, was something around 27 in 60 seconds. So that gives a sense of like it is actually like really challenging, but it's a fun example here, and it's a nice example of inverse kinematics. So I do recommend trying it. And so one thing that's interesting about the case of moving from 2 degrees of freedom to 3 degrees of freedom, and as we just did in this 3-link arm, is that we could recognize that in this case there are 3 unknowns because we have 3 revolute joints that we need to specify a configuration for. But the problem itself, the position of the end effector, has essentially 2 constraints. And so this is an underdetermined system, if you remember from our linear algebra refresher. And so as a result of that, there are many cases here where there actually will be an infinite number of solutions to the inverse kinematics problem. And so that introduces really an interesting wrinkle into this topic of inverse kinematics and how we solve for these joint configurations. So just as kind of a recap of what we've talked about, so within the Ford kinematics framework, right, we were calculating these transformations from some frame n to the world frame 0, which were functions of the configuration of the robot, specified as the joint angles, or in the case of prismatic joints, you would have the translational degree. And the result of this transformation, we can think about it as being some matrix here H, which describes both the position component of our end effector and also the rotational component describing the orientation of our end effector collectively. And so what we were then trying to do with inverse kinematics is we were essentially trying to inverse the rotational component and also inverse the position component in order to calculate the joint configurations that would satisfy some given position or some given orientation of the end effector. And so the approach that we looked at was a closed form solution, right? So in the two-link pendulum case, what this looked like was trying to calculate those joint angles using trigonometric properties of the pendulum arm, where the input to these calculations were the desired end effector position, and so this was the approach that we looked at. In the next lecture, we'll look at an optimization-based approach. So the setup for inverse kinematics will be the same in the optimization framework, just that instead of this closed form solution, we'll use a slightly more general form that will try and optimize for these joint angles. And so the next question, though, to ask is, we've looked at like these kind of planar armed robots, but what about the case of working in three-dimensional space where we have 6 degrees of freedom to describe the pose of our robot parts or our end effector? So in the case of a 6 degree of freedom position and orientation, the result of our forward kinematics is going to produce some, you can see here the rotational component now has been extended to be a 3x3 matrix, and the position component now has a third element. And so, of course, the question now becomes: is inverse kinematics still possible in this more kind of complicated and larger state space? And the answer is it is still possible. And even with a closed form solution, actually, there have been robots implemented that apply inverse kinematics in 3D space with closed form solutions. So in particular, one example is the Stanford manipulator robot, which is shown on this slide here. So it actually was implemented and can be implemented with closed form solution to inverse kinematics. So the calculations here are taken from the Spong textbook, where it actually works through how it is you can calculate each of the degrees of freedom based on some specified end effector position. And so one thing that's apparent from looking at these equations is you can see that the complexity is growing, right? So as we're moving to these higher dimensional spaces, the resulting equations that we need for our closed form solutions are also growing in complexity. And so this is very typical and what should be expected when we use these closed form approaches. They can become, they're very predictable, but they also can become more complex. So let's look at maybe what it is we could do with a robot arm that has closed form solution for inverse kinematics implemented, but exists in 3D space with 6 degree of freedom end effector pose. So here's a set of interesting examples that students from various courses within the robotics department and the EECS department here at the University of Michigan have done using the techniques for inverse kinematics that we've been discussing. So in particular, this robot here is a Rex arm robot that students use for various courses to do some really cool projects. So we'll take a look at some of the projects that students have implemented using inverse kinematics that we've been discussing. So the first one here was essentially sort of like a Pokemon kind of inspired robot where the goal was to to detect, pick, and place each of these Pokemon figurines into a desired location. And so you can see the robot here is articulating all of its joints. And so what would be specified is essentially that the robot would have some visual detection of where within space the Pokemon objects were located. The robot then would have a set point defined for where the end effector should pick up the objects in world coordinate frame. And using that desired end effector position in world coordinate frame, the robot then could know, using inverse kinematics, what joint configuration would be needed in order for the end effector to be at the correct pickup location. At that point, then, it could plan a trajectory for the pickup location using some additional techniques. And then once again, it could define a place location at what is shaped like a Pokeball, but that circular place location would then give it a set point or a desired place location in world coordinate frame, which once again, using inverse kinematics, it could then solve for the proper joint angles to execute the place action. Another cool example of inverse kinematics with these type of arms is shown here. So it's actually playing air hockey. And so once again, so basically the inverse kinematics was used for the robot to plan where the kind of like defender should position its end effector in order to block the incoming puck. So yeah, and so the last project we looked at was from students taking Robotics 550. This project is from EECS 467. So your current class, EECS 367 and Robotics 320, are precursors to EECS 467. And so this could be an example of the type of project that you could look forward to implementing if you choose to continue taking EECS 467 in the future. So another cool example, here I'll turn on the sound. So another cool example is this robot. So you can see the student there played an example of our fight song, right? So Hail to the Victors on the piano. And what this robot then is programmed to do is actually to transcribe the music that it heard into like proper formal musical notation. So you can see here it's drawing out the musical staff, and it'll then notate down which notes it heard with the correct symbols and the correct to denote the duration of the note and which actual note was played. And so this is a really neat. I think this one is really cool to me. I think this is a very, very neat application of inverse kinematics and also signal processing in a combined way. One other thing I'll point out about this video is that you can see that they have this text on the screen that this is at 2 times speed. One thing that is kind of interesting to me is like this is actually like a really common, very, very common thing that you'll see in robot demos. Typically, we have to speed up the results of our demonstrations with robots in order for the results to be kind of interesting in a timely fashion for humans, because typically our robots are slower than we would like them to be, than we can kind of wait for in terms of viewing the results as humans. And so this is very common, seeing this 2 times speed up. So once again, this is a really nice example. This also came from EECS 467 students. Another cool one, which had a great name, was Robob Ross, also from EECS 467. So this was a robotic painter. So in this case, you can see here the robot is essentially applying paint to its brush, which it can then go and paint onto the canvas. I believe the input to this robot was sort of a desired painting in the form of an image. And then based on the image, it could break the image down into a set of paints to be applied. And then from there, it could define the desired end effector position, which could be solved using inverse kinematics for the joint angles. And then once again, it could plan a trajectory using those joint angles as set points. So the robot that was used in these demos that we just looked at is what's called the Rexarm robot. And so both in EECS 467 and Robotics 550, this robot is used for projects. And so if you are interested in this robot and some of these demos looked exciting to you, I'd recommend looking at either or both of these classes as good topics and courses that you could take in the future using the foundations that we're building on in this current course. And so this particular Rexarm robot, so it's a 4 degree of freedom robot, and what we can do is we can apply some of the techniques that we talked about today for finding closed form inverse kinematic solutions to this 4 degree of freedom system. So now we started with looking at 1 degree of freedom pendulum inverse kinematics, then we moved to 2 degrees of freedom, then we briefly looked at 3 degrees of freedom, and now we're on 4 degrees of freedom. So let's look at how this system could have a solution in a closed form, and really the approach that's taken by students when they take some of these other courses for defining their inverse kinematics. So one thing we can do is we can sketch out this robot to understand the state space. So in particular, like I mentioned, this is a 4 degree of freedom robot. So it has a rotational joint around its base, and then which is here, so it can revolve around the scene with respect to the vertical axis of the scene, and then it has 3 additional rotational joints along each of its 3 links. And so together there's 4 rotational angles that would have to be solved for within an inverse kinematics routine. And so these angles then are depicted within this graphic here. So theta 1 describes, like I said, the rotation about the vertical axis of the scene. Theta 2 is then the first, we could call it like an elbow joint, the first rotational joint beyond on the first link. Then we have theta 3 describing the next rotational joint, and finally theta 4. So the end effector for this robot is positioned at the very final link. And in addition to that, what we have defined are the link lengths. So within inverse kinematics, what's going to be given to us is the link lengths. So each of the four rigid body links, where we could consider like this base here to be, in addition, a link. We also have given to us the end effector position with respect to the base frame. So this we can think about as being the end effector position in the world coordinate frame. So again, since this is a 3-dimensional space, we're going to have an X and a Y and a Z component. And finally, then, we also have given for our inverse kinematics the end effector orientation, which is going to be described as an angle with respect to the plane centered at this origin 3. So it's described here, and that's parallel to the ground plane. So that final angle here, phi, is also considered part of the end effector orientation. So the approach then that we can take to actually solve for these angles, theta 1, theta 2, theta 3, and theta 4, because again the output of our inverse kinematics should be this configuration satisfying this desired end effector pose, would be the following. So what we can do is we can break the problem down similar to how we did in the case of the 2 degree of freedom arm. So the first thing that we'll try and do is let's solve for maybe the easiest one first. So the easiest one to solve for here is going to be theta 1, right? So this revolute joint about the vertical axis of the scene, we can solve just as we did in the 1 degree of freedom pendulum arm case. So in particular, if we consider like an overhead view of the robot, we would see something like this, where theta 1 now in this bird's eye view, this overhead view, would describe this rotation here, where again the sort of vertical axis within the scene in this diagram in the upper right can be thought of as coming out of the screen, sort of towards your viewing direction. And so within this, right, so if we want to calculate theta 1, what we can recognize is that this is just very, very similar to how we calculated theta 1 in the case of the 1 degree freedom pendulum. So what we can do is we can use the inverse tangent function based on the xy coordinates of our desired end effector position to satisfy this first degree of rotation. So we've solved the first one, and then what we want to do, right, is then we need to solve for theta 2, theta 3, and theta 4. And so once again, the way that students generally will approach this problem for a closed form solution is to break these down kind of one by one. So the first thing then that we can do is we can break apart the robot arm, so we can decouple it and consider just the end effector as being kind of separate from the rest of the robot. And you can also break apart the base joint since we've solved for theta 1, and then we can consider each of these as kind of related but separate with respect to our calculations for the joint angles. And so to save some, so for the sake of our discussion here, I'm going to kind of fast forward and look at what these calculations would ultimately result in. So essentially for calculating theta 3, what we can do is we can use the law of cosines, similar to how we did in the 2 degree of freedom pendulum case, right? So if we look at just link 2 and link 3, this is based on, this is very familiar in the sense that it's the same kinematic structure as our 2-degree of freedom pendulum. And so the law of cosines can be applied to solve for theta 3. Meanwhile, for theta 2, what we can do is we can use similar trigonometric properties based on, in order to constrain for just either elbow up or elbow down. And then finally, solving for theta 4 is where we'll actually combine each of our previous solutions to, in addition to the desired end effector orientation here, in order to solve for theta 4. And so putting all of these together then would give us our final inverse kinematics solution. And so this was just stepping through it again at like a high level, just to illustrate that in these closed form techniques, what's typically common is what you'll do is you'll sort of decouple the robot and break it down into sort of simpler problems to solve one by one, and then finally put these individual solutions together to form the final output from your inverse kinematics routine. So in this case, the final output would be theta 1, theta 2, theta 3, and theta 4 composed as the joint configuration. And so the one downside of this approach, right, is, as we can see, it becomes very complex to solve. So the advantages of these closed form techniques is we have a very efficient solution, right? So in particular, all of the techniques that we've looked at today, and what's typical of closed form solutions, is that you can compute them in constant time, right? So in all of these cases that we looked at, if you just plug in the input desired position, the actual output angles are, when we say closed form, what we mean is that there's a single equation without any function calls or recursion that can result in the output angle. So this is where the speed comes from, right? So there's these constant time calculations where there's no for loops involved. We're just evaluating trigonometric functions. In addition, we have a very high degree of predictability with closed form solutions. So we can be confident that we will ensure that there will be a solution given certain constraints hold, right? So as long as there's a valid end effector position as input, then we can guarantee, for example, in the case of the 2-degree of freedom pendulum or the 3-degree of freedom pendulum, that there will be at least one solution that will be found, and it will be a valid joint configuration. The downside with closed form solutions is that they're not very general, right? So as we saw in all the cases that we looked at, the equations that we were deriving were specific to that kinematic structure that was under consideration, right? So in the 1-degree of freedom case, we derived it was only hold for the 1-degree of freedom pendulum. Similarly, for the 2-degree of freedom pendulum, the results only hold for that 2-degree of freedom pendulum. And so the challenge there is that if we want to implement for a robot operating system some inverse kinematics routine, we want it ideally to work with a sort of diverse set of robots that could be using our robot operating system, right? We don't want to have to redefine our entire inverse kinematics stack just because there's a new robot that gets kind of implemented using our robot operating system. And so this is one of the downsides with the closed form solution. The other downside is the complexity in defining, which is related, is the complexity in defining these closed form equations, because they become rather challenging as you add degrees of freedom, just as we saw in the examples that we looked at. And so to address this disadvantage, a trade-off that's made is to rely instead on optimization-based techniques. So in particular, using some iterative solution to inverse kinematics, we could potentially make a more general solver that maybe will be a little bit slower or less predictable, but we'll have that increased generality. And so typically the way that these iterative solutions will work is you'll define some notion of error with respect to the desired pose of your end effector, and the goal then of the solver will be to minimize the error between the current end effector's position and the desired position that was given as input. And so one way that we can sort of think about this is using a gradient descent approach, where you'll repeatedly take steps, right? So you'll iteratively take steps in the direction that will minimize this error until you converge at the desired end effector position, or at least until your error converges to some to some value. And so then graphically what this will sort of look like is what's illustrated in this diagram here. So if we consider that the robot in this case it has some start end effector position here, and then it has a number of degrees of freedom involved. It looks like there's like at least 4 revolute joints, potentially 5 revolute joints here. And what will happen with the gradient descent approach is if your desired end effector is here, you'll iteratively take steps that will be reconfiguring each of the degrees of freedom in order to minimize the error, which is moving you towards the desired end effector. So then what's plotted here are the various links that are rendered as you take these steps to minimize your error. Where again the result of this approach will still be a set of joint angles describing a configuration that can position our end effector at the goal position. And so looking forward, so next lecture is where we're going to be talking about these approaches to optimization-based inverse kinematics. So as a recap, today what we looked at are the closed form solutions, where we use knowledge of the robot kinematics and the geometry in order to calculate in a set of equations, a set of closed form equations, what joint configuration would satisfy the desired end effector pose. And next lecture, what we're going to be looking at are these optimization-based techniques where we'll try and minimize some notion of error between the current end effector position and the goal end effector position in order to solve for our inverse kinematics. And so in particular, what we're going to be looking at next lecture are gradient descent-based approaches. So we'll look at what's called the manipulator Jacobian as the derivative of configuration, and how we can use the manipulator Jacobian for this inverse kinematics approach. And we'll also talk about a few other approaches, including cyclic coordinate descent, which can be used for inverse kinematics as well. And so with that will conclude today's lecture on inverse kinematics. So this was our first of 2 lectures, and I'm really looking forward to seeing the upcoming new robot definitions for assignment 3. So I look forward to seeing you this week during interactive session and lab, and I'm excited about next week where we'll have the robot showcase.